Good morning, everyone. Good morning. Okay, I'll do it one more time. You can do better, right? I know it's Friday, 8 o'clock. Good morning, everyone. Good morning. Okay, that's better. So, welcome to the last day of PASS Summit 2018. Thanks for coming to this session. Again, I think this is the only session on microservices here. So, we'll talk about Monolith to microservices, how you can make a successful transition. Few of the housekeeping items, if you can silence your cell phones. Again, PASS has a lot to offer, so I would highly encourage you to go and participate, be part of few of the user groups, virtual groups, local groups, user groups which you have. Session evaluation, again, very critical for us as speakers, as PASS, as a committee as well, that you all submit your evals. Again, there's a story. I'll just take a minute. So last time when I presented here on SQL Server 2016, during this slide, I mentioned that folks who come to my session are actually somehow lucky because they tend to win the awards at the end of the day. And actually, one of the folks, after my session, after the PASS was over, he reached out to me and said that, hey, I did win a prize. So again, you might get lucky, so just make sure you fill up the evals. Something about me, I'm Samir Behra. I work as a solution architect in EBSCO Industries in Birmingham, Alabama. I also run the SQL user group in Birmingham. I hope I'll have my chapter lead sometime. Again, what I have done is all the content in this during my presentation, I have already written detailed blogs about each of the individual topics. Everything is in my website, which is .netvibes.com. So after the session, you will have the presentation slides, but you can also go to my blog in case you are interested on some specific topic. It's in-depth information on the code level, on the implementation side. You will find it there in my blog. So what are we going to cover in the next 1 hour? Well, I'm a man on a mission today, right? I have a lot of items to cover. So I want to make sure that by the time you leave this room in the next 1 hour or in the next 75 minutes, you learn something new which will help you when you make your journey from a monolith to microservices or you start working on cloud-native applications. So we will be trying to cover the differences between a monolith and a microservice. What are the issues with a monolith architecture? Why do you want to move towards microservices? How do you make that move? What are a few of the design patterns which you should be using when you think about making that hop? We'll talk also about a few of the cloud migration strategies. Again, I have been working on microservices for a good amount of time now. So all the content on this slide, whatever I'll be covering, none of those are like just theoretical concept. All of these we have implemented in our applications, and it's running live in production now. So all our learnings, which I had working on microservices, I'll just try to spread it across. So we'll get started with monolith architecture. So there are multiple companies who are they're working on legacy applications. They're working on monoliths. And it's been a challenge to keep up with the pace in which the industry is growing, right? If you're working on still legacy applications, because there's so much of technical advancement. So what are the real issues here? So as you see here, we have the user who is interacting with an order management system which talks to a monolith database. So for the purpose of this presentation, I will be using the reference of an order management system, and we will see how we can break down this order management system into a microservice, into different microservices, okay? So few of the problems which you bump into with your monolith or a legacy applications are like you have a large code base. It might be written like 10 years back. It might be on a legacy code base. You might be having so much of technical depth accrue to your applications, right? You might be having less code coverage. You might be having a lot of duplication. You might be having tightly coupled components, right? So it creates a problem when you want to deploy to production. Like, I've been part of few of the legacy applications where I had multiple teams working on a single application. We had development team, we had maintenance team, we had some enhancement team, and doing a deployment in production was a big activity. It used to take us like a month or so just to plan out a release, and then there was a full day activity. There were so many manual actions, a 10-page Word document to go step by step for doing a deployment. And we want to move out from doing that, right? We want to cut out all the manual action. We want to release features quickly to production. That's the whole purpose of doing our development. So, and then again, we are stuck with a fixed technology stack as well when we are with a monolith. So that's something which prompted us to move towards a microservices architecture. So the first step which you take when you are trying to move away from monolith is looking at the various domains from a business perspective, right? So a few years back when we used to start any development on a greenfield project, we get the requirement. The first thing was we used to design our database. Okay, we'll create all our tables. And then we used to create our classes. That entire process created few issues for us because we were not being aligned with actually the business domains. So when you start moving from a monolith to microservice, so first thing which you do is follow a design principle called as domain-driven design. This is, and per this design pattern, what you need to do is talk with your business folks, try to understand what are the domains you have, what are the subdomains, try to find out the bounded contexts, okay? And then you can start planning out how you can break that monolith. So here in the order management system, we looked at and we said that, okay, for us, the primary domain is, say, we have one bounded context as the ordering system. And then when an order is placed, I need to price that order. So pricing is one of the bounded context. And to do the pricing, I need to know the currency conversion rates. So we had currency as one of our bounded context. Once you identify all these domains, right, you can basically start thinking about, okay, for each of these bounded contexts, you can have one of the microservices. So as you see here, like for the pricing, we have, once you figure out your bounded context, you can have a specific data store assigned. Again, it can be relational, it can be non-relational, based on the requirement for that particular component. And that's something which you have to decide based on your application. But this gives you the right direction when you think about breaking your monolith. One step ahead, when we look at this diagram, we have the user interacting with an API gateway, which is just like a front door to your microservices architecture. And it takes care of authorization and all those stuff. But you see the different components here. We have an order service, title service, currency service, pricing service. But all of these have a shared monolith database. It's a good design. It's a step ahead than what it was earlier. At least we have identified the different components here. But there is a problem with this design when you have one shared database. Anyone who can think about an issue with this kind of architecture? Yes?
If you make a change to the shared database, you can potentially break all services.
Absolutely. So if you make a change, a schema change in one of the tables, you have the potential of breaking all the other teams who are working on different services. Again, there's one more thing. So say out of all these different 4 components, your order service is something which needs to be scaled. So come your Thanksgiving time, come your any holiday season, and there is a spike in user usage, right? You want to scale up order service. So in this case, it's difficult to scale because you're still tied up with a single shared database. So the only option which you have is either scale the entire database or nothing, right? You get all or nothing here. And as well, like you have this huge database, so there is a tendency that you might bump into some of the performance issues as well. So that prompted us to, okay, start thinking about breaking down the monolith database as well. One thing which we identified in our journey is it's easier to break down the code from a code perspective, the front-end code, that's easy to break it down. But when you think about breaking down the database, that's the toughest part. Data handling, how you can break down a shared database, that has been kind of very challenging for us. And we have to take few of the action items like, okay, identify your domains, and I will be covering few of the other concepts, but we will go step by step as to how we achieve that. One of the first principles which you have to follow is kind of databases are private to each of your microservices. So if you have multiple services, say you have an order service, you have a pricing service, your order service will have its own data store, pricing service will have its own data store. But point to remember is your order service cannot or should not modify any of the data in the data store of pricing service. So if you want to modify, if order service wants to modify anything on the pricing database, it has to make an API call to the pricing microservice and let that make the change. So that way, your changes will be consistent throughout your microservices architecture, right? So this is one principle which you should always follow. The databases should always be private to each of the microservices which you create. Yes, sir.
I know you should not modify the other properties, but can you order select queries that present?
So the question is, we understand that we should not be modifying the other databases, but can we fire a select query? So again, the same thing. If you want to fire even a select query, you have to make an API call to that particular service and get that information. Everything should be an API call. So on this diagram, so what we did was we identified, okay, what are the services, and then start having individual databases for each of the services. So kind of this is the ideal microservices layout. You have a user who reaches out to a UI, to a front end, and then you have different microservices. As you see, we have 4 different microservices here. Again, you have a bunch of benefits once you are able to come to this architectural design. First thing is, if you want to make any changes to the order service, you just go ahead and make that change. You don't have to worry about any of the other components out here like title, currency, or pricing. So if you want to push a change to production, you can deploy your change in the order service directly. So your deployments are faster. You are now not dependent upon other services, right? So you might be having multiple teams working on each of these services, and they can work independently. So you have basically broken down your monolith into small, independent, deployable components. And then, yes, sir?
You do need to make them backward compatible, right?
Yes. So any of the database changes, again, I'll talk about it, but any of the database changes you make should always be backward compatible. So,
I mean, even the API.
Yeah, absolutely. Yeah, including the APIs. So one of the other benefits which we have on this architectural design is scalability. If there is a particular component which you want to scale here, say the title service you want to scale, you can scale out that service, you can scale out that database, depending upon your user spike or usage. And then you can have different technology stacks. So on a microservices architecture, you are free to use any of the technology. You're just not stuck with, say, .NET or Java or Python. You can use a mixture of any of those. It doesn't matter until you are deploying your services as a Docker container, I think it doesn't make a difference. And then from a database standpoint as well, you can select your own relational or non-relational database depending upon your use case scenario. Yep, sir.
How would you handle if this were multi-tenant, so like say Nike and Reebok, they all have the ability to differentiate, somehow bring the data together between order service, title, all those. Like how would you handle that if it was multi-tenant?
So the question is, on a multi-tenant, how do you handle when you're making different calls? So there, you will need to have some aggregation logic, wherein if you want data from each of these services, you can spin up some API calls, but they need to do some aggregation once they get response from each of these services. And again, I will be talking about, it's in the upcoming slides, we'll go through those. Automated CI/CD pipeline, it's critical to have that in your microservices, right? For deploying any of your components, no matter you break down your monolith into microservices, but you need to be able to deploy your service to production, right? So you don't want manual action there. So having a automated CI/CD pipeline is critical. So in this diagram, what we have is a user checking in code into, say, GitHub, and then triggering a build. It can be either Azure DevOps, which is rebranding of VSTS, which Microsoft did like a couple of months back, or it can be Jenkins, which is a very popular CI tool. So on the pipeline itself, we want to make sure that we perform some of the automated steps for verifying the correctness of our deployments. So a few of the stages which we have here is testing. So any of your unit test, integration test, irrespective of whether it is front-end code or database code, you have to have tests around those. Quality, for testing the code quality, we have a number of tools available for doing a static code analysis of your code, and it will give you a feedback as to how much technical depth you have, how much code coverage you have. And if you're breaking any of those parameters, it will fail your deployment build itself. Deployment using Docker containers, load testing, so kind of performance testing as well. When you're pushing new changes, you want to make sure that you are not degrading the quality of the performance of your existing services. So we can run some stages there using some tools to quickly see that whether the performance is degraded or not. And then finally is security. If you want to have some security checks, you can use some of the tools to verify that as part of your pipeline as well. So on this diagram, what I have is, this is how a CI/CD microservices system looks like. So kind of hover over this. So as a developer, you can use any of the IDEs, Visual Studio, IntelliJ, on any of the language, .NET, Python, Java, SQL, and you make the changes, you push the code changes into GitHub, right? This triggers a CI build. You can use Jenkins or Azure DevOps, and then you're deploying it as Docker containers. From an infrastructure standpoint, we can use few of the tools like Chef, Ansible, or PowerShell to automate your infrastructure. You don't want to deal with that manually. And then there are a bunch of tools which you can use on your pipeline itself to make sure that you have code coverage, you have performance test, load test as part of the pipeline. And then again, you can use, if you are moving towards cloud, you can use any of the platforms. Again, all the concepts which we'll be talking about in this presentation are cloud agnostic. No matter what cloud platform you choose, you should be able to apply these principles there. And then there are a bunch of tools. Once you have your microservices in place, you want logging in place, you want metrics in place, you want to view the cost of your microservices. So you can use a bunch of tools here to monitor your microservices. So deploying monolith application. So here, what we are seeing is we have kind of the order service. We have 4 teams identified who are working on this monolith application. And as the first step, we said that, okay, let's create a CI/CD automated pipeline. And there you go. We have this pipeline there. So we should be all set for doing our deployments, right? Does anyone see a problem with this architecture, wherein we have 4 teams working on 4 different components? Again, it's still part of the monolith application, but we have segregated those components into order, pricing, title, currency, and there is a single pipeline. What can go wrong with this? Yes, sir?
Any one team can break the entire process.
Absolutely. There you go. Any one team can break down the entire deployment step, right? So say Team A makes a change, pushes those changes as part of the pipeline into your dev QA environment. Team B comes behind. They push a change too, but that code fix is incorrect. It has a defect. They push the incorrect changes through the pipeline. It gets deployed, and it breaks that environment. After that, if Team C wants to push a change, they cannot do anything, right? Because the environment is already broken. So they need to wait until Team B goes ahead and fixes that problem. So this is the problem which we have bumped into with multiple teams working as part of a single pipeline. So how do we move out from this, right? So at this point, we need to think about how we can break down this monolith. And we have a couple of options here. So if you want to break down the monolith, you can rewrite that system, right? You don't like it. Okay, it's a legacy system. We don't know who has, it was written 10 years back with legacy, with old code, old language. There are so many bad stuff about it, and you'll say, okay, let's rewrite, let's redo everything. But is that viable, right? You might take a year to rewrite that application. Business might not agree, right? Because you won't be able to deliver any new features which they won't ever approve. So, and there is a lot of effort to rewrite a monolith application as well, because there are few folks who have all those towers of knowledge, and yeah, it's a huge risk. So one pattern which we followed in our journey is strangler pattern. And what it says basically is you start incrementally breaking your monolith. You identify one component which you think is the simplest one. Again, based on your expertise, the team's expertise which you have, if you know about strangler pattern, then you can take a level up. But if you are new to strangler pattern, select a component which is the simplest one, right? If the order management system or order service is the simplest one, select that component. Or select a component which has good unit test coverage. So you'll know that when you are rewriting that application, that component, if something breaks, you will immediately know. So strangler pattern says that, okay, let's break down this monolith incrementally in small phases, one component at a time, right? You first develop your new order service component. Once that is ready, you start strangling your existing monolith. And then at some point, once the new code is 100% ready, tested, and it works fine, you can decommission the old component itself. Yes, sir?
I understand the approach. My concern with our monolith is that we have an incredible number of shared utility classes. So, I can break off the functionality of the order service, but I can't isolate it completely from the rest of my world because there's all that shared code. It's not area, it's not domain specific.
Correct. So the question is more, when we are breaking up this monolith, we might be having a bunch of shared components. So how do you handle in case you have that scenario, right? We had the same problem too, where we had a bunch of shared components which each of the services were using. So as the first go, what we did was, okay, let the shared components be there, and still the new microservice was referring to those. Then as the next step, we started putting all those components at a single place so that we can make them as probably a NuGet package and then just refer it in each of these new services. And then finally, we started breaking down seeing, okay, is it really required, all these dependencies, and how we can think about getting rid of few of those dependencies and building that as part of the microservice. This approach, I guess, at the last 5 minutes of my presentation, I will show you a good way in which we solve this problem, how we resolved the problem of shared libraries. So I will cover those as well. So here what we see is we successfully strangled this order service from the monolith, and we made it individual. And then team A is working on this order service, and we created a separate pipeline for it, right? So this order service has its own separate database, and it has its own separate automated pipeline. And that way, this component is totally independent. We can make changes on the order service as and when we need, multiple times a day. That's absolutely fine. And then we start thinking about, okay, what we can do with the other components. So once you get some expertise on strangler pattern, I would suggest go with the component where you're making the most frequent changes. So if there is a component where business, you see that in the next 6 months, you'll be making ton of changes, or there's always one component where you have some new business requirements coming in, select that component, because that will make your life easier. Not all components inside your monolith needs to be changed, right? There might be few areas which you are touching always. Take that component out. That will make your life easier. And second, try to go with a component which needs scaling. So if your requirement is, okay, you need to handle a spike in load during some point during the month beginning when you have a lot of traction coming in, or during holiday seasons, try to find out the component which needs scaling and first abstract that out from your monolith. Is a question? Yep. So it's a wrapper at this point, and it's still, the first step is a wrapper, and then you go ahead and break it down. So once you start following strangler pattern, this is where you will land up with each of the service will have its own database, having its own CI/CD pipeline. And again, in this scenario, if team B breaks a build, it will only impact them. The others are independent. They can still go through making their deployments. So kind of in strangler pattern, you will have three-phased approach. First phase is transform, wherein you are creating your new service. It will take you some time to do that development work. There is coexisting phase where both the service, the old version and the new version, will coexist for a small period of time. You can do the testing, and you can verify that the new service is working as you expect. And then finally, the eliminate phase, where you say that, okay, the new service is up and running, let's decommission the old components. So one thing here, when we talked about that pipeline, right, where one team, you had one pipeline, and you had multiple teams making changes. So there is something called feature flags. Again, it's awesome. It helps you to do continuous deployment in your production environment. So let's look at a scenario as to what are the benefits you can get if you have feature flags implemented in your system. So think about two functionalities which you want to deliver to your business. You have feature A and feature B. Feature A is small, but feature B is kind of big, and you have broken it down into B.1 and B.2. Teams, you have different teams, and you start doing your development work. Feature A and feature B.1 is ready. The development is done, and you say that, okay, I can release my code changes to production. You push it out all the way. If you have feature flags, you can push out your changes by having your feature flag turned off. You can push it all the way to production. You can test out the feature A. You can turn on the feature flag A. So feature A will be live in production. You cannot turn on the feature flag B, right? Because B.2 is still pending. The development is still going on. So you can wait. Once feature B.2 is ready, you can just turn on the feature flag B, and that functionality will be live in production. And again, it helps you to do continuous deployment even when your feature is not 100% developed. And in case there is an issue now which you find in production, if with feature B implementation, you can just turn off the feature flag, right? No rollbacks. Yes, sir.
How do you implement feature flags in SQL?
Yes. So good question. How do you implement feature flags in SQL for a database change? We want to make sure for any time you're making a database change, it should be backward compatible. You should not be making any breaking changes. Just for example, you want to rename a column, right? You have a column name as employee ID, and you want to rename it to EMP ID. You just don't go ahead and immediately rename that table or column. What you have to do is you create a new column called EMP ID in your table. You migrate all your data, right? And then at the next step, you can come and then once all your application are pointing to the new column, you can come back and delete that old column. So it's kind of expand and contract model which you have to follow in case of a SQL change. Going back to our feature flag scenario, again, we covered a good case scenario wherein we pushed something and it all went good. So what happens if while during your testing there is a defect, right? So say you have feature A and feature B ready. Everything, your development teams are done. We push the change to QA environment. Let's turn on the feature flag A. Let's turn on feature flag B. And let's do some testing. Now, we identified a defect with the feature A. So what do we do in this scenario? So we have one master branch in one of the environment. Feature A has a bug. However, business wants feature B in live in next 2 days. And I don't know how much time it takes to fix this bug. So how can we go with this scenario? Any ideas how we can fix this problem? Absolutely. So what we can do is we can, at this point, since there is a bug, we can turn off feature flag A and then just push the change to production. So in production, we'll have feature A turned off. We can create a defect and start working on the bug fix here. And then once it is ready, we'll turn on the feature flag, do a testing, and if it looks good, we can push it all the way till production, and then just turn on the feature flag, and we have both the functionalities live. Yes, sir.
So would you create a new feature flag for the bug fix, or would you just incorporate it under the original feature?
No, we'll create a new one. Or as well, thinking back, you can as well have the same flag, same feature flag. Depends upon the code changes actually. In few of the scenarios, if the changes for the defect is actually widespread across multiple pages, you have overlapping changes, it's a good option to go with a separate feature flag. Or else if the change is like a small one-liner, you can just go with the feature flag, existing feature flag B itself. Anyways, it's turned off, so it should be fine, yeah. So let's discuss about few of the architectural patterns which will help you in your microservices journey, okay? So I have primarily 4 design patterns which we'll discuss here. The first one is event-driven design. This is very critical when you are having a number of services and just to make your services available all the time. So here, in the first diagram, what we see is the order service. So you make a request to your order service. The order service makes a call to your pricing service. The pricing service calls currency service, gets a response back, pricing service does the calculation, and then passes on the calculation to the order service, and then the order service passes the order cost to the user. So the problem with this thing is, basically, if your calls are taking 2 seconds time, so basically on the front end, the user is waiting until you get a response from all the services and back. So you might be seeing a spinner like for 2-3 seconds. It's from a UI perspective, that's what is happening in the background. You are making multiple calls, few of those calls are taking time, and you see a spinner. That's not a good design because you want to make sure that your services are immediately available. So here, what you can do is you can introduce a queuing mechanism. Again, there are multiple queuing mechanisms which you can use: MSMQ, RabbitMQ. So once an order is placed by a user, you just create a message and put it on the queue. And then immediately you make yourself available to take in the next request. So from a user standpoint, they just put in a request, and immediately the system is available. Again, you are sacrificing consistency for availability in this case, right? Your system is immediately available, but you know that you have not completed the processing yet. Your processing will take few additional time, but that's happening in the background. There might be a delay of 1 second, but then you know that your system is available. So here, the advantage which we'll get by introducing a queue in between these services is, say the pricing service is down, say the database is down. What happens here in the first case? The pricing service is down here, the order service, you get thousands of requests from the user makes so many requests, and then the pricing service is unavailable. So basically, there is a chance that you are losing all those requests, right? So you will not be able to recover from that scenario. Whereas, if your pricing service database is down here, what can happen is the messages will get lined up in this queue. And once the service is up, it will automatically pick up the messages and it will process through. So having an event-based design gives you a lot of flexibility. It makes your system a lot more resilient in case of failure scenarios. Let's look at, let's go one step ahead and let's think about scalability as well. Yes, sir.
Let's say there's the pricing plan, the pricing service failed and there was a fraud or something, and we have to roll back everything. We have to say this is not an order. How does the rollback functionality work?
So rollback for a particular request, an API request?
Yeah, let's say I placed the order.
Yeah.
And the order is in the queue, right?
Yeah.
But the credit card I used was fraudulent.
Yeah.
Now you have to roll back the whole thing, right?
Yeah. So on that case, so for handling those type of rollbacks, what you can do is you can implement a circuit breaker pattern there. So what you can do is you can, if you bump into any issues during any of these services calls, you can have a fallback implementation, and you can put your own, any functionality which you want to have, you can provide it as part of the circuit breaking functionality. Again, it's there on the next slide, so let's go to that. So that the next thing is about scalability. So you have your web server, you have your order service, and then you have your database. What happens if during a holiday season, you get like 1 million requests on the first day of a month or something, right? Will your order service be able to handle it? No, it won't be able to handle that higher load. So when that higher load comes in, we have seen systems going down immediately. Okay, system is not available. So to handle that, if you have a queue-based mechanism, what you can do is you can send all the messages in this queue. So if you get 1 million requests, you can start putting it into this queue. You can have an auto-scaling policy for your queue saying that, okay, if you get more than 1 million requests, immediately scale up your instances. So you can have a policy written wherein it will keep an eye on the number of messages on the queue. Once it reaches 1 million, it will just spin up, say, 4 instances additional. And once that load is processed, it will automatically scale it down. So that's the power of having a queuing technology as well. It gives you resiliency, and it helps you to scale as well. Something which we just talked, circuit breaker design pattern. So you have, in your microservices architecture, you have like service A, service B, service A calling B, calling C, calling D. What happens if there is an issue with service C, right? You don't want your entire microservices architecture to fall down when one of your service is down, right? So if one of the services down, you still want to gracefully handle that scenario. You can't throw out saying that, okay, one of the services down and the entire system goes down. We cannot afford to do that. So when you're designing your microservices, you have to assume, or you have to always design it in such a way that it should be ready to handle any failure. So your microservices are going to fail at some point or the other. No matter how good you design it, it's going to fail because it's still a distributed system, right? It still works over network, one service calling the other. If the network is having issues, you will bump into that problem no matter how good your design is. So there, if you want to have a bit of resiliency, a bit of stability, what you can do is you can implement something which is called as a circuit breaker pattern. So here, if you see like service C, the database is down. How do you want to handle it? You implement a fallback implementation. The fallback can be anything. Say your database is down, you can say that, okay, send back a default value, or send back a cached value, or send back, or make a separate call to another service to gather that information, or send even a default message back saying that, okay, service is unavailable, check after some time. So here, once you get this fallback method implemented, what you're doing basically is you're giving your service C database time to recover. If your service is down, you don't want to keep hammering it with requests, right? So here, once you have a fallback implementation, your service is down, the circuit will just open. It will say that, okay, service is down. Until the service is up, the circuit breaker is functioning. And you have a queue in place, so you'll keep on stacking all the messages at the end of the queue. And once your database is up, the circuit will close, and it will automatically start processing the messages. Yes, sir?
I understand how that would work, like in an event-driven architecture.
Yep. Mm-hmm.
What I don't understand is how it works when you need feedback to the user that his operation failed, or that it completed in either case. How do you use a queue when the user is waiting for the response from the operation?
So the question is, a user is waiting, and and some of the operations have failed, and you want to provide that feedback, right? Okay, so that will be taken care by the API call itself. So when you,
but not if it's queued, because then it's off the queue somewhere.
yeah, there will be.
The call is done. You have no access back to the user.
Absolutely. So again, you make a call, and you have, that there is a delay which will happen, right? To cater to that request, it might take you a second, one second time to do all that process and get a proper response back. So if you have a queue as well, it doesn't mean that there will be a 5-second delay. So with this entire queuing mechanism and all these different architecture, we have a strict SLA of 2 seconds. So no matter whenever a user makes a request on the UI, no matter if that request is making call to 10 services or 15 services, we have to always send back a response within 2 seconds using a queue. That's how our SLAs are. So the user, if they make a request, we are not losing a track of that user. So the response still goes immediately. It's just that the queuing mechanism gets us more stability, resiliency in case there are any issues. So if one of the services is down, it will start queuing up. It can handle those scenarios.
I guess I'm not following. If I send out a transaction that says, create an invoice, on these items.
Yep.
The user at the screen,
Yep.
is waiting to see what the bill is.
Yep.
I can put it in a queue and it can complete whenever it gets completed.
Yep.
But the user's moved on and done something else. How do I tell him now, oh, by the way, the thing you did 5 minutes ago now has a
Okay, it's basically sending a notification back when that operation is complete. In those scenarios, the way we have implemented it is having a pub/sub model. So the user does a transaction and he moves away to a different screen. And say that particular transaction takes 2 minutes time, and we don't want the user to wait. So once that is done, what we do is we have a pub/sub model wherein once the message is processed, they will be, say, SNS and SQS. We have a SNS topic where once that operation is complete, it will get a message that, hey, this operation is complete. And that particular user has subscribed, needs to subscribe to that topic. So once that transaction is complete, he will get a notification back that, hey, whatever you did is complete. So that's kind of a pub/sub model.
I mean, in a desktop app, that sounds perfectly reasonable. In a web app, I don't quite understand.
Again, let's discuss it after the session. I will show you a real implementation of the pub/sub model, which we have. So we can talk through that just to take care of the time. So another 15 minutes. Again, I will be available after this session. So in case there are any in-depth questions, we can go through a few of the code changes as well. So next step is caching to improve the database performance. So once you are working in your microservices layout, right, you have, as I said, we have a 2-second SLA to meet any of these functionalities. For those to meet those 2-second SLA, we might be doing 8 services call. So even if your service, if one individual service is returning a response in 300 milliseconds, we will still miss the SLA of 2 seconds because we need to combine 300 seconds, and it's coming to like 2.4 seconds, and we are missing the SLAs. So there, it's very critical to have caching in place. So the way the caching work is, okay, you have a caching layer in front of your database. A user, a service makes a call. It will first check that whether the data is present in the cache. If yes, it will immediately send a response back. If no, it will then go and hit the database. It will save that response back in the cache and then send it back to the user. So basically, it's storing it in memory, which is always much faster than storing it on disk. Again, Redis or Memcache, those are a few of the very popular caching implementations which we have. Cloud migration strategy. Again, there are 2 different approaches which you can take when you are thinking about a migration plan. So the first is migrate. You just go ahead and say that it's a lift and shift approach. You have your services on-prem, your databases, and you say that, okay, based on business requirement, based on cost, based on time you have, the approach you want to go is just do a lift and shift. So you take your services, put it there in the cloud, and you're done, right? It's faster. There is no coding change required, but then you won't leverage any of the benefits of cloud because your monolith application was not designed that way, right? So the process is faster, but you won't get any immediate benefit until you refactor. So that's one approach. And the second is obviously modernize. You look at your application, you start finding out the components, what needs to be scaled. You redesign your application, keeping in mind the services on cloud, keeping in mind those functionalities, how you can scale on cloud. You keep those in mind and then migrate your application. So again, modernize, it will take you a long period of time, but you will see the benefits of, once that is done, you will see immediate benefits there. So on the cloud migration strategy, you have basically 6 R's is what an easy way to remember if someone asks you about migration strategies. So first is, again, what I've done is I've considered 3 factors here: the cost, what is the effort, and what is the time to migrate here, right? So the first thing is retire. You look at your monolith application and you say, hey, there is a component here which is never being used. Why to have that? You just retire that component. You're done, right? One component is out. So retiring is very easy. Retain. You look at your monolith application and you start seeing, hey, this guy is huge. It will take us a couple of years to rewrite this. And at that point, and business won't agree. And at some point, you'll say that, OK, let's push this to future, and let's continue with what we are doing now. So that's kind of retain. You're not doing anything. You just say that, OK, let's just postpone the cloud migration to a future point. The third effort is rehost. Rehost is just lift and shift. You take an application, put it in the cloud. Replatform is lift and shift plus some changes on the OS or from the database side. You make some tweaks to the lift and shift approach. That's replatform. Another approach is repurchase. You look at some different SaaS solutions which you have, and you try to see, okay, how we can leverage few of the products which are already available in market for our use case, and we start using those. And finally, we have refactor, which is kind of, okay, looking at the monolith, start breaking it down, re-architect it. It will take you time. It takes time to re-architect a solution, rewriting few of the components. But once it is there in cloud, you will get immediate benefits. You'll be able to deploy faster. You will be able to scale. And again, that's what business needs. If there is an enhancement coming in, you should be able to release that feature in production as soon as possible. You will be able to achieve that with refactoring. From a deployment standpoint, one very popular technique to deploy is called as blue-green deployments. And what it says is you maintain 2 copies of your production servers. So you have a blue server, you have a green server. So it's just denominator, like just saying it. But again, you have one server here, production server, and another similar server placed here. At any point, your live production, end customers, the entire traffic is going through the blue server. So this is your production server at this point. If there is a new feature which you want to deploy to production, what you do is you deploy those code changes in this green server, which is a replica of your production system. So you deploy it here. You can do some sanity testing. And once you think that, OK, it looks good, you can just switch this flip, the load balancer switch, and route all traffic through this new server. So here, the flexibility which you get is, in case there are any issues which you find out in production, there's no need of doing a rollback. You can immediately flip the switch here and start routing all the requests through the old blue server. So rollback, handling resiliency, so that's how a blue-green deployment is very helpful. If you take one step ahead, you have something called as a canary release, which is very popular with Facebook, Twitter. Whenever they release a new feature, you might have noticed that you might not be seeing that feature, but your friends might be seeing those features. So basically, they do a partial release. So what they do is you start sending a small amount. So this is your new code. This is your old code. You start sending a small traffic to your new enhancement, and you start gathering feedback. You start capturing metrics and see that, OK, what's the response from the customers who have got the new feature. And if it is good, you start changing it. So start sending 20%, 30%, 40% of the traffic to the new system. So that's something canary release, which we do in our production systems. Works great. Again, but you need to have some monitoring, automated monitoring in place to capture the feedback once you start routing traffic to your new users. So the next thing which we'll look at is 3 pillars of observability. Again, we talked about, we broke down our microservice into 15 small, we broke down our monolith into 15 services, but we want to make sure that we are having logging in place, we are having metrics in place, and then we are also having tracing in place. What that means is, in case there are any issues, I should be able to immediately go back to my logs and find out which microservice is a problem, or troubleshoot a issue with a particular microservices. So logging will help there. Metrics is something, if you want to see, OK, what's the CPU utilization, what's the memory utilization, what's the response time on one of my microservice. So all those different parameters, how many number of messages are there in one of my queues. So all those things comes under metrics. You have a number of tools which you can use to actually get those metrics. There's no need of coding. You can use any of the tools available. And then for tracing, so your service you have a 2-second SLA on the UI, and you have like 8 service calls which you are making. So you want to, if the overall request takes like 6 seconds, you want to figure out which service is the culprit here, right? So the first service might have taken 200 millisecond. There is a third service which is taking 6 seconds. You want to trace that out. So it's very important to have tracing in place so that you figure out as your calls, API calls are going through each of the service, how much time each of the services are taking to respond back. Monitoring your microservices architecture. Again, we see here that we have order service, pricing service, title service. All are logging to a centralized repository. Centralized logging is in place. You are collecting all the metrics. You need to have real-time monitoring. You cannot do manual monitoring on your services anymore since you're having 20 or 30 of them, 30 microservices. How do you manually monitor? No, you have to have real-time automated monitoring. You can create few of the dashboards if you want to have some visualization at any point. If you want to monitor a particular service, you can create one dashboard, and it will give you all the statistics as to how that service is functioning. And then you need to have alerts and notification. If your pricing service is down, immediately in next 5 minutes, your development team needs to be notified that, okay, one of the services has gone down. So you can implement few of the toolings to have an automated monitoring in place. Yes, sir?
Doesn't that become your single point of failure then, if you've got centralized logging?
So the question is, doesn't it become a single point of failure if you have centralized logging? Again, each of the application needs to have logging in place. You need to use a library, and you are logging it to say we use Sumo Logic for logging, and what they do is just get all the logs from all the services, and that will give us a dashboard to just view all the logging at one place. Again, yes, it is. To answer your question, all these tools are a single point of failure as well, because if any of those say repos go down, you will stop having logging in place. Yeah. Going next to visualization and time series analytics. Again, this is what I was talking about from having your own dashboards for each of the individual microservices. So this is using Grafana, but what you do is you create this dashboard. It comes out of the box. Once you just configure a few of the metrics, and you get this dashboard for each of your microservices. And you can come here, log in, and you get all the metrics. Okay, CPU, memory, how's the processing time, what's the infrastructure things going on, SLAs, all the things you can view at one place. Distributed tracing. Again, as I was saying, one service makes call to another service, makes call to another service. So we should be able to track what is the latency between each of the service calls. So there's where we can use few of the tooling to capture this information. So here, as you see, the blue boxes are all the microservices, different microservices. And I make a request, and it goes through all the services. And you see on the right how much time it is taking to cater to one request. So whichever is the longest one, that's taking more time. So that's tooling which you want to have in place if you want to troubleshoot any performance issue with your microservices. Code quality. SonarQube is kind of the best static code analysis tool at this point. The best part about is it has predefined rules. It's free. It has predefined rules for each of the different programming languages. You can configure your own quality gates, and in case few of your say unit tests are failing or you are dropping down code coverage, it will automatically fail your build. So you will get an immediate feedback if you are breaking any of your quality standards. So here on the left you see a all green dashboard of SonarQube, and then on the right there are so many reds where the build has failed because we introduced new issues as part of the latest code change which we pushed to master branch. Testing, again, we need to have automated testing in place, and it's just not unit test which is sufficient once you go into a microservices architecture. You need to have multiple layers of testing in place, automated testing in place. So we'll start from the bottom. Unit test, testing one component, right? Integration test, trying to test multiple components together. Code quality check is through SonarQube. You do a static code analysis of your tools. performance test, you use any of the tools to load test, to do a performance test for your application. Contract test. This is interesting because what it says is, if service A is making a call to service B, in order to get a response from service B, it needs to send 3 parameters. And if it sends those 3 parameters, it gets 2 parameters back. That's the response. If as part of any change, if you are not sending those 3 parameters, you are not abiding to the contract, and your contract will fail. So that's kind of some of the tests which we have when each one microservice is talking to another. End-to-end test, you want to make sure that from the API, from the user interface level till all the services which are there, you are able to end-to-end test your system. Resiliency test, it's something called as chaos engineering. And what you do is, you have your microservices architecture, you knowingly bring down one of the database, and then you see what's going on. Obviously, you don't do it in production. Do it in dev environment, and just see how your microservice architecture is behaving in case there is a unexpected failure, and how you can recover from it. And then accessibility test. If you have a user interface, you want to make sure that people with disability as well are able to access your user interface. So you can use some of the toolings to have that. So again, we talked about so many complexities, right? So these are few of the issues which you will have once you'll get all the benefits in a microservice architecture, but then these are the issues which you will end up with. You'll have to take care of service discovery, circuit breaking, versioning, health checks, observability, management, metrics. All these things needs to be in place for each of your microservice to be functional. That's the problem, right? You have your business functionality, and then each of the microservices needs to have all these components so that other microservices can interact with it. So this is the problem which we landed up when we moved from Monolith to microservices. And that was where I was coming to when you asked about the shared libraries. We started seeing that, okay, for small new microservices which we are developing, the development might be just like thousands line of code, but all these different functionalities, to get all these different things in place, we were using third-party components, having so much of additional coding just to take care of all these infrastructure components. So it was like we were 1,000 line of business code and 10,000 lines of additional coding to get all this functionality in place. So what we did was, okay, we started creating a scaffolding project. We said that, okay, we will create one shared library saying that, okay, this is a shared microservice generator which we have, and this will have all these different components in place. So whenever a new team comes to start their own microservice, they can take this microservice generator and they can get a scaffold application, and this will give them an automated pipeline. It will give them service discovery, circuit breaking, everything is in place as part of that default scaffolding project. And then you can start adding your own code base. So we did that. It worked great for some period of time, but then we bumped into another issue. The issue was, our code base was getting convoluted with the same repeated code. Every microservice we go, we have like 10,000 lines of code, common code to implement those functionality. And developers had to maintain those. It was very challenging to see, okay, whether that code is correct or not. How do developers have to be aware of all those tooling in place? They need to be aware of all those 20 toolings which gives you one functionality each. So we wanted to move away from that approach. So something which helps you there is a sidecar design pattern. This is a very popular design pattern now, which is being followed in the microservices world. What it says is you're basically moving all your complexity from your microservice layer to a sidecar proxy. So each of your microservice, you see here 3 microservices, they will just have business functionality. It won't have any infrastructure-related functionalities. All the load balancing, all the circuit breaking, all the metrics, all those things are now part of the sidecar proxy. Okay, so each of the microservices will just have a sidecar proxy. Again, this proxy is not something which you have to create. We can use some of the proxies which are available. Envoy, which has been created by Lyft, is a very popular proxy which is currently being used in microservices world. That's something which we are using at this point as the sidecar. And moving one step ahead, so just to answer that question on shared libraries. So on the left-hand side, we had this kind of architecture earlier, wherein each of these microservices had business logic and shared libraries. We moved to a service mesh, right, wherein we got all the microservices here, and then we just plugged in a sidecar proxy. And that's something which we don't have to maintain. It's an automated, it's an out-of-the-box component which we get from Envoy, and we use Istio. Istio is another implementation of Envoy. And it makes our life so much easier because we don't have to deal with any of the infrastructure changes. We just want to deal with, as developers, we just want to deal with the business functionality, and we want to leave out all those additional complexity to this sidecar. So this has been, in one slide, this has been our journey on the service mesh side. We started with a monolith. We broke it down to microservices. When we broke it down to microservices, we saw so much of code duplication, all those shared libraries being a headache. So we took one step ahead, and we moved to a service mesh journey. So on the left-hand side, as you see, we have like few of the, this is just for one of my project, and again, based on the toolings which you have, these platforms can differ. But for platform management and platform orchestration, we had Amazon ECS. You can have, if you're on Azure, that's fine. Containerization, you can use Docker. Runtime operation, we have some tooling for having those monitoring, logging, telemetry, right? Service operation, we can use few of the libraries. And then code libraries is, okay, which language you are coding on, Java, .NET, SQL, Python. So earlier, for us, we had to code these first three things: the code libraries, the service operation, the runtime operation. So basically, the coding as well as the infrastructure was something which we had to code. And after going to a service mesh side, what happened was we used Envoy and Istio, which gives you all those functionalities out of the box. So that's something which happens on the infrastructure side now, and you don't need to be worried about any of those parts. So all you need to be worried about is just your code. That's how easy it becomes once you start going towards a service mesh side. So again, what we saw was monolith to microservices to a service mesh. Again, if you are trying to start with start your journey towards microservices, you know this complexity which you have with microservices. You can as well jump directly from your monolith to a service mesh journey and skip all those complexities associated with microservices. Again, it's a big journey, right? I compressed a lot of concepts inside 1 hour. But this took us like multiple years to have this system in place, to have the automated pipeline, to convert this monolith into microservices, to go towards service mesh. It took us multiple years. So you know the concepts at least at this point. You have my contact. If there are any questions, you can always reach out to me. But I think we are on time. Are there any questions? Yep, go ahead. Absolutely.
Covered how to break up the code quite a lot.
Yep.
But you didn't really cover how to break up the database.
Yep.
So one of the questions I had is, you said that each service should have its own private database.
Yep.
That doesn't really mesh well with the standard relational model and data integrity and things like that. You know, like, for the example you gave, you had like an ordering service, pricing service, currency service.
Yep.
Currency service, I can see how that would be individual. You're talking just exchange rates, X, Y, and Z. But for the ordering service and the
pricing, yeah.
pricing one, then it's kind of like, well, I'd need to know what the customer was.
Yeah.
So for each private database, would I keep a copy of like a customer table in each one? How do you actually take a large database that has a lot of referential integrity
Yeah.
and break that into microservices?
Yeah, that's a good question as to on a real world production system where you have customers, you have orders, you have pricing, how do you break it down and how do you maintain that relationship as well, right? So first thing, again, customer, as you mentioned, that has to be a separate database altogether because you need to think about when you are redesigning your monolith database, you just need to think about what are the different domains, right? Customer is a separate domain. I can just have the list of customer inside a customer data store. It needn't be aware of what are the orders as well. You can tie it up in some, say, the order database. There, you can have some tie-up with one customer. Okay, these are the 1,000 orders which that customer has. So that relationship has to go inside somewhere. In this case, we have it inside our order service where we know that, okay, this order is associated to this customer. Again, it's relational, yes. There might be some scenario where you can have a non-relational requirement as well. You can put it there. But yeah, all this referential integration, again, we are maintaining it by putting it into different relational databases.
So that's what I thought he was going to say. So that leads me to the question of, are you hinting that I would essentially have one database with one table in?
Yep, it's not a bad thing, again.
But it is, at least from a traditional database standpoint. I mean, if I'm going to write a query that does that, and especially if I think down the end of the line, like ETL,
Yeah.
how am I going to get that into a data warehouse?
Yeah, absolutely.
I'm then going to have to query 1,000 databases to go and get that information.
Yeah, so again, the question is, now to get a single record, I have to make multiple calls here, right? You make a call to the customer, you make a call to the order service. So again, it all depends upon the design of your application and how you are breaking down. If you think that customer and order shouldn't be broken down, have it in one store. So that depends upon you. We have figured it out as well. So when we started minutely breaking down, we landed up in the same problem wherein to cater to one request, we had to make 5 calls and then aggregate it as part of one service. And there, where we thought, okay, this is just not possible of doing it. So we started combining few of the data stores. So again, so that's where I had on my first slide. Second slide was on domain-driven design. Be very careful. Spend most of the time on domain-driven design as to how you want to break down your database. If customer, order, and pricing as well makes sense for you to have it in one store, have it that way, so that you are just not making multiple calls to cater to one request. Yes, sir.
We actually started the domain-driven design and microservices.
Yeah.
We have some success, some failure.
Yeah.
And we actually never end up finish all. So we end up stuck in the middle. So my question is, I know there's lots of cost to start the microservices.
Yeah.
Somehow I think the whole architect. My question is, on what size of an organization you recommend using microservices?
So again, size of, I think it all boils down to the size of your application. How big is that application? How big is your team who is working on those services? Like the ideal team size working on these microservices is like 5 to 6 members. That's what we have, like 5, 6 members working, taking the bottom line of one of these services or multiple services. So we don't want to cram too many people having dedicated to one service. So it all depends upon that application, how huge it is, how many development teams you have working on that, and how quickly you are able to currently deploy your changes to production, right? If you have an application which you are working on, 10 teams are working on, and it's taking you 2 months to deploy to production, you need to start thinking about a strategy again.
So if you have like 10 devs, you're saying that's too small a group to even try this?
Again, so how big is that application? And once you start breaking it down, like think about from a strategy perspective. With 10 members, you just try to figure out how much time it is going to take you to at least break it down to the microservices level. If that's taking you 1 year time or 2 year time, yeah, that's something which you want to push back or add more devs there. Again, people are leaving, but thank you all for coming, and hope you all have a good rest of the summit. Yes, sir, we can go.